Welcome to the Deep Dive. Our mission is to take a vast stack of cutting-edge research, really everything from atomic-scale defect thermodynamics right up to functioning device performance, and synthesize the absolute core knowledge you need. Today we are undertaking a deep dive into what might be the single most structurally flexible and functionally adaptable class of materials in modern material science, perovskites. Okay, let's try and unpack this a bit. We're talking about a chemical family defined by the simple formula ABX₃. And this one family is somehow driving the next generation of solar cells, complex computer memory, high-performance catalyst, and exotic magnetic sensors. It's almost unbelievable versatility.
It really is. And what's fascinating here is how that deceivingly simple formula, A and B are the positively charged causations, X is the anion, usually oxygen or maybe a halide. It masks this profound physical complexity that this class of material truly is the ultimate chemical chameleon, because you can swap out virtually anything at the A and B sites and introduce these precise tiny amounts of defects. You gain this incredible atomic level control over pretty much every single property, electrical, magnetic, ionic, catalytic, you name it.
Right. And that structural flexibility is really the engine here. Our listener wants to thoroughly understand those tuning mechanisms. So our mission today is to go far beyond just the definition. We really need to unpack precisely how these slight geometric tweaks, these specialized synthesis routes, and the intricate management of atomic defects, especially those oxygen vacancies we hear so much about, how they translate into the astonishing performance that defines the material's gold rush happening in this field right now. Okay, let's start with the foundation. The ideal perovskite structure. You often see it drawn as a perfect cube. But in reality, perfection seems pretty rare, right? And maybe it's the imperfection that gives these materials their power.
That's a critical distinction, yeah. We define the ideal perovskite structure as cubic, belonging to the space group PM3 metals. In this ideal setup, the B site rotation is perfectly nestled within 6 surrounding X anions, forming this pristine corner-shared BX₃ octahedron network. Beautifully simple. But in real-world scenarios, due to changes in composition, temperature, or pressure, the structure almost instantly starts to distort. It just doesn't stay perfect.
So those BX₃ octahedra, which are kind of the fundamental building blocks, they start tilting or rotating, maybe compressing a bit. And this distortion is what creates all those different actual structures we see. Orthorhombic, tetragonal, rhombohedral.
Exactly. The material is always seeking energetic stability. If the ions don't fit perfectly into that ideal cubic box, the structure compensates. It rotates those octahedra to relieve the internal strain. Material scientists see a general tendency. If you raise the temperature, you pump in more thermal energy, you allow the system to relax back toward that higher symmetry. You might even get the cubic structure if the composition allows it and the temperature is right. But, we rarely operate devices at those high idealized temperatures. We operate them down here in their distorted, highly functional states.
Okay, so we need some kind of rule book, a mathematical tool maybe, to predict if any given combination of A, B, and X ions will even form a stable perovskite structure in the first place. Or are we just, wasting our time trying? That's where this geometric thing comes in.
The tolerance factor. Precisely. We use the Goldschmidt tolerance factor, usually written as T. It really is the geometric gatekeeper. This factor is a simple but, pretty powerful ratio comparing the ionic radii, the size of the ions A, B, and X. The formula is T equals Ra plus Rx divided by the square root of 2 times Rb plus Rx.
Okay, looking at that formula, you're basically comparing the distance between the A and X ions to the distance between the B and X ions scaled a bit. So what are the magic numbers? What range does that need to be in?
Right. For a stable perovskite structure to actually form, T must strictly fall between 0.75 and 1.00. If T equals 1, bingo. You get that perfectly stable, ideal cubic structure, 0 internal strain. Everything fits just right. But as T deviates downwards, say E is less than 1, the A occasion is effectively too small for the space it's supposed to occupy in that cubic structure. The result is that the entire lattice compensates by initiating that structural rotation or, more commonly, tilting of the BX₃ octahedra. This tilting helps the structure kind of collapse slightly around the smaller A ion, bringing the X anions closer to it, which stabilizes the packing. If T gets too low, though, below about 0.75, the tilting becomes so severe that the perovskite structure itself just breaks down. It transforms into other crystal structures, like ilmenite, for instance.
Okay, makes sense. And what happens if the A ion is too large, if T goes above 1?
Good question. If it is greater than 1, the structure is effectively being stretched too much. Tilting the octahedra doesn't really help relieve that kind of strain. Instead, the structure tends to shift away from that nice corner-sharing arrangement of octahedra. It often adopts hexagonal structures where the octahedra are forced to share faces instead of corners. And this geometric change, corner sharing versus face sharing, is absolutely fundamental. It completely changes how electrons can hop between B sites and how ions, like oxygen, can move through the lattice.
That structural impact really needs a clear example. Let's go back to those manganese oxides you mentioned.
Okay, perfect example. Take calcium manganite, CaMNO3. The calcium ion, Cali2 plus air, is relatively small for the A site. This results in a tolerance factor T that's slightly less than 1. So to stabilize the strain, the MnO6 octahedra tilt relative to each other. This gives us an orthorhombic derivative structure, not the ideal cubic one. And this tilting is critical because it lightly kinks the MnO-Mn bond angle, which makes it a bit harder for electrons to hop efficiently between the manganese ions. It affects conductivity. Now let's switch out that relatively small calcium ion for the much larger barium ion, Ba2 plus air, to get barium manganite, BaML3. That difference in ionic radius immediately pushes the tolerance factor to well above 1. The strain is now expansive, it's stretching the structure. Tilting can't fix this. So the structure essentially gives up on the Perovskite arrangement and collapses into a hexagonal geometry, characterized by those face-sharing MnO6 octahedra.
Wow, so just swapping one divalent cation for another, calcium for barium, is enough to completely flip the entire geometric arrangement. You go from corner-sharing octahedra to face-sharing ones. And that fundamentally changes everything. Conductivity, magnetism, that really captures the essence of tuning via the tolerance factor. Okay, so once we've used the tolerance factor to check if our desired compound is likely stable, the next huge step is actually making it. Fabrication. Our sources kept emphasizing that the end application really dictates the synthesis route. A dense, strong material for something like a fuel cell needs a totally different fabrication strategy than, say, a high surface area catalyst.
That's absolutely right. It's the classic materials scientists trade-off. Are you trying to maximize geometric control and crystallinity, or are you trying to maximize surface area? You really can't achieve both perfectly with just one method.
Okay, let's explore controlling shape first, specifically targeting those one-dimensional or 1D materials. What techniques let us make perovskite nanowires, and how is that shape actually controlled?
Yeah, for getting really high-quality, single crystalline 1D materials like nanowires or nanorods, the workhorse method is often hydrothermal synthesis. This involves reacting precursors in water, but at high temperatures and pressures, usually in a sealed vessel called an autoclave. The critical factor for forming nanowires, rather than just getting spheres or random particles, is controlling the reaction kinetics, specifically the dissolution and recrystallization rates. And this is achieved primarily by carefully tuning the pH of the solution. For instance, to produce those nice uniform 15 to 30 nanometer diameter nanowires of cubic lanthanum strontium cobaltite Law 0.6 SR 0.4 CO3 delta, researchers typically use highly alkaline environments. They add mineralizers, which are usually strong bases like NaOH or KOH. These promote directional anisotropic crystal growth. The high alkalinity creates specific surface energy conditions on the growing crystal faces, which makes the crystal prefer to grow fast along one dimension, say the 100 direction, while growth on other faces is inhibited. That leads to the nanowire shape.
That sounds pretty intricate, getting that directional control just right. Is there a simpler, maybe more affordable route if you just need basic shape control, maybe not perfect single crystals?
Oh, absolutely. For more large-scale or cost-sensitive production, molten salt synthesis is often the chemical engineer's go-to method. It's generally highly cost-effective, versatile, and easier to scale up. Basically, you mix your metal oxide or salt precursors in a low melting point inorganic salt, like sodium chloride or potassium sulfate mixtures. When you heat this mixture, the salt melts, acting as both a solvent for the precursors and a medium for crystal growth. By carefully controlling the heating profile and especially the cooling rate, you can influence the final morphology. You can get nanocubes, nanospheres, or even things like barium titanate, BaTiO3 nanowires pretty cheaply this way, though, as you said, maybe with less crystalline perfection compared to hydrothermal methods sometimes.
I found that little story in the research stack about the early nanowires quite revealing. It feels like a great cautionary tale for material scientists working in this area.
It really is, and it's a constant reminder that characterization is absolutely paramount. In some early literature, several groups reported they'd successfully synthesized lanthanum manganite, LAM 0.58, 0.5 MnO3 nanowires using hydrothermal methods, looked great under the electron microscope. But then, upon more rigorous subsequent analysis, using techniques like detailed X-ray diffraction, it turned out the nanowires weren't the target perovskite material at all. They were actually simpler wire-like nanocrystals of lanthanum hydroxide, LaMOH3, just a precursor phase that hadn't fully converted to the perovskite structure. Yeah, that slight slip in characterization definitely set back research for a bit. It highlights that just because something looks like a nanowire under a SIM doesn't automatically mean it has the crystal structure and properties you intended. You have to prove it.
Right. Okay, let's shift gears from shape to porosity. For applications like catalysis, we often want an enormous surface area, not just in one dimension, but in a structured three-dimensional network. How do we build materials that are almost like an atomic scale sponge?
For that, we engineer what are called three-dimensionally ordered macroporous materials, or 3-DOM structures. The main technique uses hard templating. So imagine taking a tightly packed arrangement of tiny identical spheres. This is your colloidal crystal template, usually made of a polymer like PMMA or polystyrene microspheres. They pack together like tiny billiard balls. Then you infiltrate the empty spaces, the voids between these spheres, with your liquid metal precursors for the perovskite. After the precursor solidifies in those gaps, you heat the whole thing up to burn away the original polymer spheres. What's left behind is a perfect negative replica of the template, a highly porous, interconnected structure that looks a bit like an inverse opal architecture. Really beautiful structures.
That sounds elegantly simple in concept. Fill the mold, cook it, the mold disappears, leaving the porous structure. But our sources pointed out a really critical failure point, often involving the precursors themselves. What goes wrong?
Yeah, the main challenge, especially when you're working with lanthanide-based perovskites, is the thermal instability of the metal salts, often used as precursors, things like metal nitrates or acetates. The temperature you need to completely burn off the polymer template, which is typically around 500, 600 degrees Celsius, is often high enough to cause these metal salts to melt or decompose too quickly or react aggressively before the perovskite structure has properly formed and solidified. If that happens, the ordered macropore structure collapses. The walls break down, the pores fuse. You just end up with a disordered chunk of material, completely destroying the inverse opal architecture you worked so hard to build. It's a common problem.
So how do chemists get around that? How do they stabilize those metal precursors against this premature structural collapse during the template removal?
The solution involves using advanced chelating agents or organic complexing ligands. Things like oxalic acid or EDTA are common examples. Their job isn't just to dissolve the metals initially. They chemically wrap around the metal ions, forming a highly stable, often non-melting gel or complex within the narrow pores of the template before heating. This complexing agent essentially acts like a chemical scaffolding, locking the metal components rigidly in place, stabilizing the structure. Then, when you heat it, the PMMA template decomposes and burns off first at a lower temperature. Only then, at a higher controlled temperature, does the now solidified metal complex decompose and crystallize into the final ordered perovskite structure. This sequential decomposition is absolutely crucial for success.
And the refinement of this technique is going even further now, right? It's not just about creating these large macropores anymore. It's about creating porosity within the walls of those pores.
Exactly. That's kind of the next frontier. The holy grail now is creating hierarchical structures. 3-DOM materials where the walls themselves are also riddled with much smaller mesoporous features, typically pores in the 250 nanometer range. This is usually achieved by using a dual templating approach. You combine the hard template, the PMMA spheres, with a soft template, often a block copolymer surfactant like pluronic P123, which self-assembles into nanoscale structures within the precursor solution that fills the macropore walls. When both templates are removed, you get this incredible structure with both large, ordered macropores for easy access and mesoporous walls providing ultra-high surface areas, sometimes exceeding 100 square meters per gram. That's a massive surface area, highly desirable for things like heterogeneous catalysis.
Okay, so if the crystal structure is the chassis, then the atomic defects, especially vacancies, are like the engine, particularly when we talk about energy devices like fuel cells. We absolutely have to dive into the physics of how these materials transport oxygen ions. That's where so much of their value lies in energy applications.
Right. The foundational application here is definitely the solid oxide fuel cell, or SOFC, cathode. Also, things like oxygen separation membranes. For these intermediate temperature devices, say 600, 800 degrees C, to work efficiently, the cathode material must be a mixed ionic electronic conductor, or MIEC. This means it needs two things simultaneously. First, excellent electronic conductivity, typically targeting over 100 Siemens per centimeter to efficiently transfer electrons to or from the reaction sites. And second, it needs very high mobility of oxygen ions, O2, through its lattice to transport the oxygen fuel.
And since oxygen ions are pretty large, they can't just squeeze through a perfect solid lattice, right? They rely entirely on having gaps or holes in the structure of those oxygen vacancies.
Yeah.
That's exactly right. Oxygen transport in these perovskites is entirely dictated by the concentration, usually denoted by delta in the formula like ABO3, and the mobility of those oxygen vacancies, which we often write as VO with 2 dots, VO psi, to show their effective positive charge. Critically, the concentration of these vacancies in doped perovskites like lanthanum, strontium, cobaltite, La1, XArcsCO3 isn't fixed. It's not just set by the doping level, it's a dynamic thermodynamic property. It's highly sensitive to temperature, and maybe most importantly, it depends strongly on the external oxygen partial pressure, PO2, the concentration of oxygen gas surrounding the material. Yeah, a key principle in defect chemistry for these oxides is that the equilibrium concentration of oxygen vacancies tends to increase as the external PO2 decreases. This is actually why SOFC cathodes often perform best under the somewhat lower PO2 conditions created at the cathode surface by the electrochemical oxygen reduction reaction itself. The reaction helps create the vacancies needed for transport.
Okay, let's get right into the heart of it then, and compare the different transition metals people use on the B site. Why are some B-site cations like cobalt or iron inherently better at hosting these crucial oxygen vacancies than others, like manganese?
This is a really fundamental difference, and it comes down to the energetics, basically, the energy penalty the material has to pay to create those vacancies. Let's compare the manganites versus the ferrites and cobaltites. For manganites, where B is manganese, Mu, under the relatively high PO2 conditions typical of an airside SOSC cathode, the material strongly prefers to compensate for the charge difference introduced by the A-site dopant, like SR2 plus replacing Lo3 plus, electronically. It does this mostly by oxidizing some Mn3 plus ions to Mn4 plus ions, creating electron holes rather than ionically by creating lots of oxygen vacancies. They tend to exist in a thermodynamic region where the oxygen vacancy concentration is kept quite low. The energy cost to pull an oxygen out of the stable MNO lattice is just too high under those conditions. So they're generally poor ionic conductors compared to the others.
Okay, so the material sacrifices ionic conductivity to maintain charge balance using electron holes instead. And the ferrites and cobaltites, they flip that preference.
They do, largely. Ferrites, BAFE, and especially cobaltites, BSU, are generally superior MIECs because, under typical cathode operating condition, moderate temperature, moderate PO2, they exist in what defect chemists call the mixed compensation region, sometimes labeled region 3rd in defect diagrams. The iron and cobalt B sites have highly favorable redox potentials. This means the B site tackard can easily switch between multiple oxidation states like C4 plus matter O3 plus matter SO2 plus. This easy switching means the material requires much less energy to accommodate the charge imbalance by creating a high concentration of oxygen vacancies, even under moderate PO2 conditions where manganites wouldn't. The resulting high vacancy concentration, high ore, combined with relatively high mobility of those vacancies, translates directly into orders of magnitude better oxygen ionic conductivity compared to the manganites. They are essentially designed thermodynamically to be defect-rich.
Okay, so we understand the bulk material properties now. But then why do the sources put so much emphasis on the huge performance leap observed when these materials are engineered into nanocomposites? If the bulk perovskite is already optimized, shouldn't adding a second phase like Syria just dilute the performance?
Yeah, that seems counterintuitive at first glance, doesn't it? But we are finding more and more that the overall device performance often isn't dominated by the bulk properties anymore, especially at nanoscale. These nanocomposites, typically made by physically mixing the perovskite phase, like LSC, lanthanum, strontium, cobaltite, with a different oxide that has good ionic conductivity, but maybe poor electronic conductivity, often a fluorite-structured oxide like gadolinium-doped Syria, GDC. They exhibit oxygen chemical diffusion coefficients that are astonishingly higher, sometimes an order of magnitude higher than the pure perovskite phase alone.
An order of magnitude. Wow.
This huge boost is now widely attributed to the creation of atomic superhighways at the interfaces. The lattice mismatch and the resulting strain, plus the tendency for charge redistribution, base charge effects, at the perovskite fluoride interfaces, create regions of high disorder and significantly enhanced vacancy concentration right at the boundary between the two materials. Oxygen transport is then dramatically accelerated along these interfaces, effectively bypassing the potentially slower diffusion pathway through the bulk of either material. This phenomenon really demonstrates that for optimizing real energy devices, we're increasingly engineering the interfaces and boundaries, not just the bulk materials themselves.
Okay, let's transition from energy transport to chemical transformation. Let's look at catalysis. Perovskites are known to be incredibly stable and active catalysts for major industrial reactions, things like NO reduction in exhausts or methane oxidation. The sources seem very clear. There are two fundamental prerequisites that must be met for a perovskite to be a successful catalyst.
That's right. It boils down to two key things. First, you absolutely must have the physical site for the reaction to occur. This typically requires the presence of an oxygen vacancy, VO, on the catalyst surface. This vacancy acts as a site to absorb oxygen or one of the reactants initiating the process. Second, and just as vital, the B site cation within the perovskite must be able to undergo an easily proceeding full redox cycle. This means there has to be efficient electron transfer between the reactant molecules and the catalyst. For example, the B site cation, say Bn+, must be easily reduced to Bn1+ by accepting an electron from a reactant and then readily oxidized back to Bn+ by giving an electron to another reactant like oxygen. That cycle is essential for turnover.
So, if that redox cycle is kind of the heartbeat of the catalyst, how do engineers make that heartbeat stronger or faster? How do they boost the activity?
Well, the primary tool is again through precise cation substitution, usually on the A site, but sometimes the B site too. Let's consider lanthanum manganite, LaMNO3, as a base. If we substitute some divalent strontium, Sr2+, onto the A site in place of the trivalent lanthanum, La3+, we achieve two beneficial things simultaneously. First, to maintain charge neutrality, the substitution promotes the formation of more oxygen vacancies, which we just said are needed for reaction sites. Second, the substitution forces some of the manganese on the B site to increase its oxidation state, promoting the formation of the highly active Mn4+ species alongside Mn3+ below. This A site doping enhances both the electronic conductivity, which helps the redox cycle, and increases the number of active surface sites, vacancies, and higher oxidation state becations, often dramatically boosting the overall catalytic activity.
Makes sense. But the real world, industrial processes, they're messy. Catalysts don't last forever. They deactivate. What are the two main chemical enemies that tend to kill perovskite catalysts in applications like exhaust treatment, and how are researchers trying to fight them?
Yeah, deactivation is a huge practical issue. The two primary culprits frequently encountered in exhaust streams are water vapor, H2O, and sulfur dioxide, SO2. Now, water vapor deactivation is often, thankfully, reversible to some extent. The research suggests that, for example, lanthanum cobaltite, LaCO3, is generally more resistant to water poisoning than lanthanum ferrite, LaFeO3, or lanthanum manganite, LaNO3. This is likely due to a combination of factors. The inherent stability of the CoO bond might be higher, and cobaltites naturally tend to have more abundant native anion vacancies, which might be less susceptible to forming strongly bound detrimental surface hydroxides that block active sites. Furthermore, researchers found that adding a small amount of copper Co as a dopant into the LaCO3 lattice could further improve its resistance to water vapor. The thinking is that the Q substitution helps stabilize even more anion vacancies, effectively making fewer prime sites available for the problematic H2O adsorption.
Okay, water is one thing. But SO2 sounds like a more serious threat, partly because the sources mentioned it can sometimes permanently ruin the crystal structure itself.
It is definitely more insidious, partly because its mechanism of attack actually changes depending on its concentration. At relatively low concentrations, say below 20 parts per million ppm, SO2 tends to undergo reversible chemisorption onto the surface, oxygen vacancies. The catalytic activity dips because those sites get blocked, but it often recovers if the SO2 is removed from the feed stream. However, when the SO2 concentration gets much higher, maybe up to 80 ppm or more, which can happen in some industrial exhausts, the reaction changes. The SO2 starts to react aggressively with the A-site company, like LANAs, and the lattice oxygen itself. This leads to irreversible structural destruction through the formation of stable, bulky, and non-catalytic sulfate compounds on the surface, like lanthanum sulfate, LaNS2SO43. While some partial regeneration might be possible by heating the catalyst under strongly reducing conditions, the underlying structural damage often means the catalyst performance is permanently compromised. So the challenge here is really engineering A-site cations or surface coatings that are intrinsically more resistant to sulfate formation without simultaneously poisoning the crucial redox activity happening at the B site. It's a tricky balancing act.
Right. Let's pivot slightly to environmental remediation, specifically Econox adsorption trapping nitrogen oxides. The research shows that perovskites might solve a major problem that plagues current Econox adsorbent materials, poisoning by carbon dioxide or carbonation. Why are traditional adsorbents so susceptible to CO2?
Yeah, traditional lean NOx traps, often based on materials like barium compounds supported on alumina, especially related to Y-BAQO systems used in superconductors, rely on forming surface nitrates to store the NOx during lean, oxygen-rich engine conditions. But the problem is, if CO2 is also present in the exhaust, and it always is, these materials have a strong thermodynamic preference to react with CO2 to form highly stable, inactive surface carbonates, like barium carbonate. Once the surface is covered in carbonate, it can no longer effectively absorb NOx, and the trap is essentially deactivated. Since CO2 is ubiquitous in exhaust, this is a massive practical limitation. Perovskites, though, offer a potential workaround, again through clever structural and chemical tuning. Certain alkali metal-doped perovskites, for instance barium stannate, this NO3, or cesium-doped lanthanum manganite, LaLo.8CO0.2 MnO3, show remarkable resistance to this carbonation problem. The key seems to be that the alkali metal dopant, like cesium, tends to segregate to specific surface sites, and its presence there actively inhibits the nucleation and growth of that stable carbonate phase. So instead of getting poisoned by forming carbonates, the surface remains available to form the desired active nitrate add species for NOx storage. This allows these perovskite-based materials to maintain excellent NOx absorption capacity even when operating in realistic exhaust environments with high CO2 concentrations.
That is a brilliant example. Using one doping strategy, adding cesium to fundamentally change the preferred reaction pathway on the surface, completely bypassing a major industrial hurdle. Very clever. Okay, we've covered energy transport and chemical reactions. Now let's jump into pure solid-state electronics, where perovskites exhibit some really fascinating, sometimes quite strange phenomena. Let's start with colossal magnetic resistance, or CMR, in the manganites.
Right, CMR is one of the hallmark properties of doped manganites, like the classic lanthanum calcium manganite Lo1xKxMMO3. In these materials, the electrical resistivity can plummet sometimes by several orders of magnitude when you simply apply an external magnetic field. It's a huge effect. The traditional understanding, the standard picture, is that the maximum resistivity occurs near the Curie temperature, TC. That's the temperature where the material transitions from being a highly conductive ferromagnetic metal at low temperatures to a much less conductive paramagnetic insulator at higher temperatures. The peak resistance happens right around that magnetic phase transition.
But the research we looked at shows this confusing anomaly. An unexpected second resistivity peak often appears, called the low temperature peak, or LT peak. It shows up far below TAC, especially in samples like thin films or nanocrystals. And crucially, this LT peak doesn't seem to be associated with any clear structural or magnetic phase transition happening at that temperature. So what's going on?
Yeah, that LT peak puzzled the field for quite a while. But the deep dive into the material sources, especially looking at studies on inhomogeneous samples, provides a pretty cohesive explanation now. The phenomenon appears to be a direct consequence of inherent structural and electronic inhomogeneity within the material. The key idea is that the material, especially when it's nanocrystalline or a thin film with lots of grain boundaries and defects, doesn't exist as just one single uniform phase below TSE. Instead, it's better described as a complex mixture of phases coexisting over a surprisingly wide temperature range. You essentially have islands or regions of the high resistivity paramagnetic PM insulating phase still persisting, mixed in with growing regions of the more conductive ferromagnetic FM metallic phase as you cool down below TSC.
Okay, so it's like a patchwork quilt of conducting and insulating regions. What does this patchwork structure mean for how electrical current flows through it?
Well, think of it like a traffic jam scenario for the electrons. As the temperature drops below TC, the volume fraction of the conductive FM phase starts to increase. Naturally, the electrical current prefers to flow through these low resistors metallic channels. But if the sample is highly inhomogeneous, say, a nanocrystalline sample with a lot of insulating grain boundaries, or surface layers that remain paramagnetic, you still have a significant volume fraction of that insulating PM phase acting as barriers or bottlenecks scattered throughout the material. The LT peak occurs at a temperature where the current flow becomes increasingly constricted by having to navigate around or tunnel through these numerous residual insulating barriers, even though the core FM regions are becoming more conductive. The overall resistance goes up temporarily because of these bottlenecks. So the peak isn't really a fundamental bulk phase transition itself, but rather a macroscopic performance anomaly dictated by the degree of disorder, the connectivity of the FM phase, and the interface resistance between the FM and PM regions in that specific inhomogeneous sample.
That's a really neat synthesis. The material's failure to be perfectly uniform is actually what creates its unique and initially confusing electrical signature. Fascinating. Okay, Let's switch gears now to high-density memory components, specifically using the dielectric properties of materials like barium-strontium titanate, or BST.
Right, BST, ba-SOFCs, and related materials like pure ba-TiO3 are crucial dielectrics, especially in thin film form for applications like capacitors in dynamic random access memory, DRAM. Their value comes from two key properties. They have a very high intrinsic dielectric constant, epsilon, which means they can store a lot of charge in a small volume. And importantly, that dielectric constant is strongly dependent on an applied electric field. This property is known as tunability. High tunability means you can significantly change the material's capacitance just by applying a relatively small voltage. That's essential for creating high-density switchable memory elements.
And the research details two highly effective methods for boosting that tunability, making the material even more sensitive to the electric field. What are they?
Okay, the first main strategy is chemical substitution. A common approach is to dope the A site with a small amount of lead, Pb. Adding lead does a couple of useful things. First, it can be used to carefully shift the ferroelectric phase transition temperature, Tc, where the dielectric properties change most dramatically, so that it sits right near the intended operating temperature of the device, often room temperature. Operating near Tc generally maximizes the material's sensitivity to an electric field, hence maximizing tunability. Second, this kind of doping often introduces what's called a diffuse phase transition. Instead of a sharp transition at Tc, the transition gets smeared out over a broader temperature range. This actually helps give the device more stable and predictable tunability across a practical range of operating temperatures. The second key method is a processing technique, electric annealing. This is quite clever. It involves applying a strong DC electric field while the BST thin film is undergoing its high-temperature annealing process, which is needed to crystallize it properly.
Why does applying a voltage during the annealing help? What's it doing physically?
What the electric field does during annealing is it physically influences the displacement of the central titanium T-ion inside its surrounding oxygen octahedron, the TO6 unit. The field encourages the Ti-ion to shift further off-center as the crystal structure forms and cools. By essentially locking the Ti-ion into a more asymmetric, more significantly off-center position during the fabrication process, you increase the initial polarization and, in a sense, the stiffness of the ferroelectric lattice. Then, when a smaller operating electric field is applied later in the device, it finds it energetically harder to further shift that already displaced Ti-ion. This resistance to further shifting manifests as a larger, more stable change in the dielectric constant relative to the applied field, in other words, enhanced tunability. You're physically pre-biasing the atomic structure to enhance the macroscopic field response.
Very interesting. Finally, for electronics, let's revisit our friend the oxygen vacancy. But this time in the context of memory switching. Perovskites, like zirconium-doped BST, are showing promise for non-volatile resistive switching memory, sometimes called ReRAM. How do those same oxygen defects end up controlling the storage of digital ones and zeros?
Yeah, the switching mechanism in many of these perovskite oxide ReRAM devices seems to be dominated by a phenomenon called the space charge limited current, SCLC mechanism. Unlike some other switching mechanisms that rely on forming conductive filaments, SCLC is considered a bulk-limited effect. It's defined by how injected charge carriers, usually electrons, move through the material and, crucially, get trapped and released from defect sites within the bulk. And the primary trap sites are, once again, the oxygen vacancies. The oxygen vacancy, being effectively positively charged, VRS, acts as an attractive trap for electrons injected into the thin film from the electrode. The switching between the device's high-resistance state, HRS, and low-resistance state, LRS, appears to be governed almost entirely by the ionization state of these oxygen vacancy traps, essentially. How many electrons are trapped in them and how tightly those electrons are bound.
Okay, let's look at the activation energies given in the sources. They seem to quantify this difference quite clearly.
Exactly. When the memory device is in the high-resistance state, HRS, maybe representing a 0, the electrical conduction is found to be dominated by the energy required for the second ionization of the oxygen vacancies. This implies that the vacancies are likely doubly occupied with trapped electrons, and freeing them up to contribute to current flow requires overcoming a relatively high activation energy barrier, the sources quote around 0.63 electron volts, EV. It takes significant energy to get electrons moving, hence the high resistance.
And the low resistance state flips that situation.
Precisely. When the device is switched into the low resistance state, LRS, the conduction mechanism changes. It becomes dominated by the energy associated with the first ionization of the oxygen vacancies. This suggests the vacancies are now only singly occupied, or perhaps there's a network effect. Freeing this first electron requires a drastically lower activation energy, around 0.093 eV, according to the data. This much lower energy barrier allows for much easier electron transport, possibly along chains of these partially filled vacancy sites, leading to the low resistance state. So the memory state, the 0, 1, is literally stored in the quantum mechanical ionization state of the electrons trapped at these oxygen vacancy defects within the material.
Okay, to wrap up our tour of applications, let's briefly look at the optical realm. Perovskites are increasingly regarded as important optoelectronic materials used in LEDs and detectors now, too. But their light emission doesn't always seem to follow the simple rules of typical semiconductors. Where does the glow actually come from in many pure perovskites?
That's a good point. The photoluminescence, or PL, the light emission you see when you excite the material with higher energy light in pure, undoped perovskite oxides, is rarely due to a simple direct band gap recombination like in classic semiconductors, for example, GAAs. Instead, the emission is nearly always traced back to those same structural imperfections we keep talking about, primarily oxygen vacancies and various surface defects. These defects create localized electronic energy states deep within the material's band gap. When the material is excited, say by UV light, electrons and holes get trapped at these defect states. The light emission we then see results from electronic transitions between these localized defect energy states and the conduction or valence band edges, or even between different defect states. For example, those lead titanate PBTiO3 nanowires we mentioned earlier show a distinct blue light emission band centered around 471 nanometers. This emission is strongly linked to radiative recombination involving these localized defect states, not a simple band-to-band transition.
Amazing. So the exact same type of defect that's responsible for conducting ions in a fuel cell or trapping electrons from memory is also responsible for emitting light in an optical device.
It really highlights the ultimate structural and electronic continuity. And once again, morphology, the physical shape and size of the material, matters profoundly, even in determining how efficiently the generated light can actually escape the material and be detected. For instance, when perovskites are used as host lattices for optically active rare earth elements like europium U3+, doped into barium zirconate, BeziER-RO3, to get red light emission, the shape of the host particles dramatically impacts the measured PL intensity. Research has clearly confirmed that preparing the material as well-defined, isolated spherical particles consistently results in the highest measured emission intensity, compared to samples made of irregular particles or cubes or highly agglomerated chunks. This is likely a straightforward optical physics effect. The smooth, curved geometry of the spherical particles minimizes unwanted internal light scattering and reduces reflection losses at the surface. This allows more of the light generated inside the particle to escape efficiently and reach the detector. Shape controls light extraction.
And finally, kind of bringing things full circle from high-tech back to more basic industrial needs, we saw research showing that perovskites are even being developed and used as simple ceramic pigments for color.
Yeah, this really speaks to their superb thermal and chemical stability. Certain perovskite structures, specifically those based on tribalancations like A3 plus B3 plus O3, are proving to be excellent bases for new, highly stable, and often vividly colored ceramic pigments, especially in the red and orange range. Key examples include the lanthanide ferrites, like YFeO3 or GDFeO3, often reddish-brown, and the chromium-doped lanthanum aluminates, LNAL1-CRXO3, which can give intense reds. These materials are highly valued in the ceramics industry because they offer excellent color retention and very high thermal stability. This means they won't degrade, fade, or change color even when subjected to the extremely high temperatures used in ceramic firing processes, often well over 1,000 degrees C. And the added bonus is that many of these colored perovskite pigments, like the lanthanide ferrites, also happen to possess interesting magnetic properties, or the aluminates might have photoluminescence. This opens the door for potentially creating smart or multifunctional coatings and pigments in the future. Color plus function. #outro no light.
Wow, this has been an absolutely incredible deep dive. We started with what looks like a deceptively simple ABX₃ crystal structure, and we've seen how it acts as this amazing geometric chameleon, its very existence and form, governed by the Goldschmidt tolerance factor. We've explored synthesis methods that sometimes require really complex chelation strategies just to stop the precursors from melting before the structure forms. And ultimately, we discovered again and again that the key to unlocking its incredible potential in almost every single field, from solid oxide fuel cells to catalysts to electronic memory, even to light emission, often comes down to controlling that single critical atomic scale feature, the oxygen vacancy.
I think the unifying takeaway here is really the exquisite level of control we can gain by understanding and managing these atomic defects. It's fascinating that the same oxygen vacancy concentration that dictates how fast oxygen ions can move across a fuel cell interface at high temperature is, when localized in a thin film at room temperature, the very electron trap responsible for flipping a memory bit between a 0 and a 1. This unified role of atomic scale defects is truly the essential common thread that connects all these seemingly disparate high-tech fields built upon the Perovskite structure.
So we'll leave you, our listener, with this final provocative thought to mull over. If the subtle quantifiable energy difference between the first and second ionization of a single oxygen vacancy, just 0.63 versus 0.09 eV, can fundamentally flip a material from a high-resistance state to a low-resistance state, representing a stored bit of digital information, what other unknown, perhaps even more massive, properties are just waiting to be unlocked simply by gaining finer control over the exact location, the local chemical environment, and the dynamic behavior of those same ubiquitous defects? This ongoing quest for mastery over the atomic structure, defect by defect, is precisely why the Perovskite research effort remains one of the most exciting, dynamic, and potentially rewarding frontiers in material science today. It really is a materials gold rush.